Alright, welcome everyone. In this video, we're going to introduce the ideas behind Helmholtz and Gibbs free energy. So where these came from, and the need to kind of define these Helmholtz and Gibbs free energy is related with the second law of thermodynamics, right, which states that a spontaneous process is only spontaneous if the entropy change in the universe is greater than zero, right? So if I want to know if something is spontaneous, I got to measure the entropy change in the universe to do so, okay? And that can be very annoying and very difficult to do because that requires measuring or calculating or finding out the entropy change in the surroundings, which is not something that we can easily measure, right? And so ideally what we want is we want something that's defined for the system and the system only that will tell me about whether or not a reaction is spontaneous, okay, or some process is spontaneous, okay. And that's where we get into Helmholtz and Gibbs free energy, where these quantities are defined in such a way that they will tell us about the spontaneity of a process with measuring just quantities for the system, okay. And so again, right, we want to measure the system only. So let's consider an isothermal constant volume system, okay? In this case, right, the work that's done for expansion is equal to zero because it's constant volume, okay? That means du is just equal to dq, right, assuming no extra work. That's from our first law of thermodynamics, okay? That means dq of the surroundings is just minus dq of the system, which is just minus du of the system. Okay, so that means the reversible change in the surroundings is minus du of the system. Okay, and then so ds of the surroundings, right, plugging in for what dq reversible of the surroundings is just equal to minus du divided by t. Okay, so ds of the universe, right, which is defined as ds of the system plus ds of the surroundings, right, is going to be ds of the system, right, minus du divided by t, right? Right, again, du is the system, t is the temperature of the system, right, ds for the system. Okay. So for something to be spontaneous, right, that means ds of the universe has to be greater than zero, which means ds minus du divided by t has to be greater than zero for something to be spontaneous at constant temperature, constant volume conditions. Okay. We multiply the entire equation by t, we get this equation t ds minus du is greater than zero for a spontaneous process, okay? Right, and if you want to essentially multiply everything by a minus sign, you get du minus tds has to be less than zero for a spontaneous process. And so based off of this, we define what's called the Helmholtz free energy, A equals u minus ts. Okay, right, and so under constant temperature volume conditions, okay, delta A being less than zero tells us something is spontaneous, okay, right, and then that's because, right, under constant volume temperature conditions, right, ds universe equals minus dA, okay, and again, A is defined as u minus ts, okay, dA, right, is going to equal du minus tds, right, for constant volume and temperature, right? So constant temperature means that T is just a constant, right? And this is our definition of the Helmholtz energy, right? And Helmholtz free energy then tells us, right, if something is spontaneous for a constant volume temperature process, okay? If the process is not done at constant volume and constant temperature, Helmholtz free energy tells us nothing about spontaneity, okay? All right, let's consider an isothermal constant pressure system, okay? Right, so isothermal constant pressure, dq equals dh, okay, so no extra work. Again, we show that, right, for, right, that's also assuming mechanical equilibrium, right, that is true, okay. So dq of the surroundings, right, is then just minus dH of the system. So again, ds of the surroundings is then just going to equal minus dH of the system divided by the temperature of the system, which again is a constant value. I then again look at the fact that ds of the universe basically becomes ds of the system minus dH of the system divided by T. For a spontaneous process, all of that has to be greater than 0. Multiplied through by T gives us T ds minus dH is greater than 0. Multiplied by essentially a minus sign gives us dH minus TdS is less than 0 for a spontaneous process. Okay, and so we define the Gibbs energy as H minus Ts, right? And again, for an isothermal process, that means dG equals dH minus T ds, okay, which equals minus ds of the universe, okay? And right, so that means for a constant temperature pressure, change in state, delta G being less than 0 tells us our process is spontaneous, okay? Right, and again, that's because it's equal to negative ds of the universe, okay? Right? And so that's why we care about Gibbs free energy so much in chemistry. It's because, again, in chemistry, our chemical reactions are typically done under constant temperature, constant pressure conditions. And so in that case, the Gibbs free energy tells us about the entropy change in the universe, okay, which tells us whether or not something is spontaneous. Okay? So again, under constant temperature conditions, that change in Gibbs free energy is equal to the change in delta H minus T delta S, which we've seen before in chemistry classes. Right, so finally, just talking a little bit more about this relationship between delta H, delta S, and delta G, okay? You can think about when reactions are spontaneous at, say, high and low temperatures or high and low pressures, right? So if we think about how the spontaneity changes with temperature for a chemical reaction, right? Question is, right, is delta G less than 0? Because if it is, then it's spontaneous, okay? Well, if delta H is less than 0, and delta S is greater than 0, then this will always be spontaneous, okay? Right? But if delta S is less than 0, that means I have minus a negative number, which gives this to be a positive number. And delta H is greater than 0, that means that's a positive number. I have two positive numbers, which means delta G is always positive, which means that process is never spontaneous, okay? And then for delta S greater than 0, it's only spontaneous at high temperatures. Okay, when delta H is greater than 0. That's because you have this competition then between some positive number and minus some other positive number, right? And as long as this second positive number is larger than the first, then this will be negative, right? And to increase the size of that second number, you increase temperature, okay? And that's why when delta S is less than 0 and delta H is less than 0, that type of process is only spontaneous at low temperature, okay?